When measured values of physical quantities are used in calculations of other physical quantities, it is necessary to account for their precision, because it determines the precision of the calculated results. Let's say the mass of some object is measured and reported as 341.200 grams. Why is this number written with two zeros that follow the last non-zero digit, referred to as trailing zeros, not simply as 341.2 grams? Writing the number in such a way indicates the precision of the measurement that allowed getting 5 certain digits, 3, 4, 1, 2, and the first zero, and one further estimated digit, the second zero. Remember, when reporting measured values, we always report all certain digits and one extra estimated digit. Together, these digits are called significant digits. Values of measured physical quantities should be reported in scientific notation. Apart from being convenient for writing very large or very small numbers, scientific notation has a further important advantage. Assume that a measured value is a large number. For example, the distance from the Earth to the Moon that has been measured to be about 384,402,000 meters. The thing is, we don't actually know the distance from the Earth to the Moon with precision to a single meter. The trailing zeros here are simply used to indicate the order of magnitude of the number, hundreds of millions. In scientific notation, however, the order of magnitude would be indicated by 10 raised to some power, so we could only keep significant digits in the number that is multiplied by this power of 10. For instance, if the distance to the Moon were known with precision up to 1,000 meters, we would report it as 3.84402 times 10 to the 8th power meters. And if it were known with precision up to 100 meters, we would report it as 3.844020.10 to the 8th meters. In both cases, we would only be reporting significant digits, all but the last one certain and the last one estimated. When we report a number in scientific notation, we can and should always write it so that all the digits, including any trailing zeros, are significant. When we perform calculations that involve measured values of physical quantities, we must keep track of how many significant digits we know for each quantity. Imagine that we know the distance between points A and B with precision to meters. Let's say it's 325 meters. And the distance between points B and C along the same line with precision to hundredths of a meter. Let's say it's 23.24 meters. If we were to calculate the distance between points A and C using these known values, with what precision would we know the value of the result? Pause the video and think about it for a few moments. It is quite easy to see that we can't calculate the distance between points A and C any more precisely than we know the distances between points A and B and between points B and C. Measurements of physical quantities are always approximate. So when we say that the distance between points A and B was measured to be 325 meters, what we really mean is that it is approximately 325 meters. In actuality, the instrument that we used to measure this distance showed that it had some value between 320 and 330 meters, and we estimated that it was roughly halfway between 320 and 330, or about 325 meters, with 5 being the estimated digit. A more precise instrument was used to measure the distance between points B and C. So we were able to see that this distance had some value between 23.2 meters and 23.3 meters. we saw that it was close to halfway between these values, but a little closer to 23.2 meters, so we estimated it to be about 23.24 meters, with 4 being the estimated digit. Now consider adding these two distances. The last digit for the distance between points A and B is not certain but estimated. We think that this distance is about 325 meters, but we might well be off by a couple meters. Our measurement instrument just wasn't precise enough to know for sure. If we added 23.24 meters and wrote the answer as 348.24 meters, the digits following the decimal point wouldn't be meaningful, because if we are not sure whether we know the number of meters between points A and B exactly, we are also not sure whether we know the number of meters between points A and C exactly. Certainly, we can't know the number of tenths or hundredths of a meter between points A and C in this case. In general, when adding two numbers, we report the result only to the order of magnitude of the estimated digit for the summand that is known least precisely. In the current example, we report the result with precision to meters, namely as 348 meters, where the last digit 8 is estimated. When performing calculations in chemistry, we write all values in scientific notation. For instance, in the example we have here, we would write 325 meters as 3.25 times 10 to the second power meters, and 23.24 meters as 2.324 times 10 to the first power meters. Then, to calculate the sum, we first rewrite the summand that has the smaller order of magnitude, so that the power of 10 is the same as for the summand that has the larger order of magnitude. Then factor out the power of 10. In our example, 3.25 times 10 to the second power meters plus 2.324 times 10 to the first power meters equals to 3.25 times 10 to the second power meters, this summand is unchanged, plus 0.2324 times 10 to the second power meters, where we have changed the power of 10, so it's the same as in the first summand. And that equals to 3.24 plus 0.2324 in parentheses times 10 to the second power meters, where we have factored out 10 to the second power. Now, when we perform the summation in parentheses, we only keep so many digits after the decimal point as in the summand with the fewer number of digits after the decimal point. So 3.25 plus 0.2324 times 10 to the second power meters would be rounded to 3.48 times 10 to the second power meters, where we have kept 2 digits after the decimal point, because the first summand, 3.25, only has 2 digits after the decimal point, although the second summand, 0.2324, has 4. The same procedure as for addition is also used for subtraction. When performing multiplication or division, the procedure for keeping track of the number of significant digits is different. Let's say that we need to calculate the area of a rectangular room. The length of one wall of this room was measured to be 460 centimeters, and the length of the other wall was measured using a more accurate instrument and found to be 325.5 centimeters. To obtain the area of a rectangle, we need to take the product of its sides. If we rewrite the two lengths in scientific notation, this product will be 4.60 times 10 to the second power centimeters times 3.255 times 10 to the second power centimeters. But how many significant digits should we keep in the answer? I am not going to demonstrate it, but the general rule for multiplication is that you should keep as many significant digits in the answer as in the term with the fewest significant digits. In our case, the first term has 3 significant digits, 4, 6, and the trailing 0. And the second term has 4 significant digits: 3, 2, 2, and 5. Therefore, in the answer, we must keep 3 significant digits. So our product is 1.48 times 10 to the 5th power centimeters squared, where we have rewritten the product in scientific notation. Notice that when we multiplied the two lengths, we got 14.835 times 10 to the 4th centimeters squared, or 1.4835 times 10 to the 5th centimeters squared, but we rounded this answer to 1.48 times 10 to the 5th power centimeters squared, because we have only 3 significant digits for the first term. Further notice that when we multiplied the two lengths, we multiplied not just the numerical values, but also the units, centimeters, to get the units of area, centimeters squared. To practice unit conversions, I suggest that you convert these units to meters squared. The same procedure for keeping track of significant digits as for multiplication is also used for division. Note that when adding or subtracting two numbers, we keep track of the number of digits after the decimal point, and when multiplying or dividing, we keep track of the number of significant digits. In calculations, we may also deal with exact numbers. Common examples of exact numbers are conversion factors between different units for the same quantity. For example, by definition, 1 meter is exactly 100 centimeters. If we had to convert, say, 2560.4 centimeters to meters, we would multiply the number of centimeters, 2560.4, by the length of a centimeter in meters, 0.01 meters. We would rewrite these numbers in scientific notation. So we would have 2.5604 times 10 to the 3rd power multiplied by 1 times 10 to the minus 2nd power meters. And we would get our answer as 2.5604 times 10 to the 1st power meters, or that would be the same as 25.604 meters. If we were multiplying two approximate numbers, we would need to use as many significant digits in the answer as we had in the term with the fewest significant digits. However, when one of the numbers in our calculation is exact, we may assume that this number has infinitely many significant digits. For instance, 1 centimeter is exactly 0.01 meters, by definition. In other words, we know that all digits following the 1 are zeros. 1 centimeter is 0.010000 and so on meters. Therefore, the number of significant digits for the result of any arithmetic operation where one of the values is exact will always be determined by the number of significant digits for the number that is known approximately, typically a measurement result.